Welcome to Lesson 9, Refraction and Optical Fibres. This is the last lesson in the Waves and Optics section. Here's the plan for today. It's really important that we draw light consistently. A quick but vital habit first. We draw light as straight rays, and every angle we measure is taken from the normal. That's the dashed line drawn perpendicular to the surface at the point where the ray hits. A lot of students lose easy marks by measuring from the surface instead. Always measure from the normal. Another, less common way that light is drawn is with the wave fronts being lines perpendicular to the direction of propagation. You can think of these as looking down on the transverse wave of light, and these lines are the tops of the waves. I like the metaphor of these being tank tracks, and we'll see their use in deriving Snell's law. Make sure you know the difference between these two. Refraction is light bending as it changes speed when crossing a boundary. We describe each material by its refractive index n, which is the speed of light in a vacuum divided by its speed in a material. This means that the speed of light in the material is the speed of light divided by n. Since we cannot exceed the speed of light, n is always greater than 1, and the n for a vacuum is equal to 1. A bigger n means the material slows light down more. Let's look at how we derive Snell's law. The image on the left shows your classic drawing of light rays, and the image on the right has a portion of that which is the same. But what we want to consider is the lines which make right angles with the red lines. Remember, these can be thought of as the peaks of the wavefronts. These are the tank tracks, and we can think of this as a tank driving at an angle from a surface like tarmac to a surface like mud, in which it moves much slower. This means that the tank tracks which reach the mud first are slowed down, but the ones that haven't reached it yet keep going at the same speed, which means that the tank turns. This is how we can think of the light turning towards the normal as it changes mediums. Now let's consider the angles involved. From symmetry, theta I can be re-expressed in relation to the red line, so can theta R. The relationship that we get is that sine of the incident angle equals c1t, which is the speed of light in the first medium. This also equals ct over n1, which means that n1 sine of the incident angle equals ct. From the same process, this also equals n2 times the sine of the refracted angle. Equating these gives n1 times the sine of the angle of incidence equals n2 times the sine of the angle of refraction. This is Snell's law, and is one way to derive it. Now for something that only happens going the other way, from a dense medium towards a less dense one. As you increase the angle, more and more of the light reflects back inside, and at a certain angle, called the critical angle, all of it reflects internally, either by reflecting at the same angle or being refracted along the boundary. Beyond the critical angle, no light escapes. That's total internal reflection. The critical angle is given by sine theta c equals n2 over n1, and if the outside is just air, that simplifies neatly to sine theta c equals 1 over n. This can be derived nicely from Snell's law, since we make the angle of refraction equal to 90 degrees. Total internal reflection is what makes optical fibres work. A fibre has a high index core surrounded by a lower index cladding. Light enters and keeps striking the core cladding boundary at an angle above the critical angle, so that all the light is totally internally reflected, over and over, all the way down the fibre, even around bends, if the angle that it is bent around is not too steep. The cladding isn't just decoration, it protects the core and stops the signal leaking or crossing over into neighbouring fibres. We use these for communications, for medical endoscopes and the internet. There is a problem that arises with these optical fibres that we need to be aware of: dispersion, which means that over time, the sharp light pulse smears out along the fibre. There are two kinds. Modal dispersion comes from light rays taking slightly different path lengths down the fibre, so they arrive at slightly different times. Material dispersion comes from different wavelengths of light travelling at slightly different speeds in the glass. Both effects blur the pulse over long distances, which is why fibre design works hard to minimise them. That's the end of the video and completes the topic of waves in optics. Next time we move into mechanics, starting with forces and vectors. Thanks for watching. Check out my tutoring page below.